We're going to be talking about Macho dark matter in particular, and a particular type of dark matter. So that's what we're going to talk about, Macho dark matter. And why Macho dark matter? Like, why am I bringing this up now? The reason I'm bringing up Macho dark matter right now is because it's related to the black hole that was discovered, the rogue black hole that was discovered, like 2 weeks ago. So let's dig into it. Where do I want to start? Let us start with the rogue black hole. Let me pull up constraints on what I'm looking for. This is probably it. I think this is it. So this is the paper that came out on the archive. It's archive 2201.13296 for those who want to look it up. And it's from data taken with the Hubble Space Telescope. So it's got a gigantic author list of like 8 million people. So every scientist on the planet, except for me, was an author on this paper. I'm scrolling up to the top, scrolling up to the top, scrolling up to the top. Okay, so now a lot of these people are fairly standard. Like Kalish here, he's the Galactic Center Hubble Space Telescope guy. He's been doing stuff with the Galactic Center using Hubble for a very long time, like looking for planets, all this kind of stuff. And there's a bunch of other people here that also, I actually know more of these people than I thought. So Rachel Street, for example, she does exoplanet stuff. Keith Horn is a guy from the UK who does, it's all photometry. It's like taking images of distant objects and looking for changes in the brightness of these distant objects. That's what most of this stuff comes from. And so there's the main authors up here, and then there's several groups of people who are looking for changes in the brightness of different objects. So if I can maybe zoom in a little bit, I don't have a whole lot more room to zoom before everything escapes the size of the screen. But like the Ogle collaboration, that's the optical gravitational lensing experiment. Planet, I don't know what that is, but I know what they do, which is they look for exoplanets because of microlensing events. So you have, I'll get into the physics of what's happening there, but they're looking at photometric signatures of planets. Same thing here with microlensing fun. All of these are different groups of people who are looking for changes in brightness of distant objects, and the places where they concentrate their telescope time is either towards the galactic center, because there's a lot of stars there, so you get a lot of targets that you can look for changes in brightness, or they will look for towards the Large Magellanic Cloud, which also has a large concentration of stars. Okay, and in particular what they're going to be looking for is if you have an observer over here. So here is us, the observer. And here is a distant star. Okay, there's a distant star there. And as an intermediate object passes along the line of sight, then when the two things line up, so they have to line up to a very small precision, like they have to be really close to being aligned. What will happen is the gravitational influence of the lensing object, so this is the lens, this is the target. So you have a target star in the distance, you have a lens that intervenes along your line of sight. And when the lens lines up with the target and your eyeball, then you get light, well, that was not what I meant to draw. You get light focused from the distant target around the lens. And so instead of just getting light that only comes along the line of sight, you also get some light that is away from the line of sight that gets lensed back towards you. And as a consequence, this will brighten. So as the lens passes along the line of sight, the brightness of the target will grow like this and then go back down. So this is the kind of signature that people are looking for. If there's a planet going around the lens, so suppose the lens has a little planet going around it, then you will often see a little bump like this as the planet also produces a lensing signal. That's a terrible bump. Let me do a different bump. There, you'll get a bump like that as the star that is the lensing star, and the planet also can produce a lensing signal as it orbits around the star. So you don't actually observe the lens. You observe the target star, and you infer the properties of the lens based upon the nature of this change in brightness that you get. So that is the kind of signal that these things are looking for, and that is, let's see, what church do I belong to? I belong to the Church of Jesus Christ of Latter-day Saints. All right, if we scroll down here, we can see and a couple things happen. They also, not only does the lens make the target look brighter, but it can also shift the position of the lens. So if we're looking along the line of sight and here's the distant target and the lens is here, let's see, the lens would actually be, okay, let's see, what's a good way to draw this? So here's the target. we're looking kind of a top view now. Here's the target again at a different time, and here's us at a different position. And you have this lens that goes by. When the lens comes by, you can actually get the light predominantly coming towards the line of sight from one side versus the other side. And so it will displace, when you look, it will look as though the distant target actually shifts slightly to one side, or once it passes by, it might shift slightly to the other side. And so that's what they're showing here, is the shift in milli-arc seconds of the position of the star that they've been monitoring. So here is the shift, and then when the lens is directly aligned, then the shift goes away. And then the shift is predominantly to the other side as the lens continues to go by. And then the amplification, that's the brightness. So as the light gets brighter, you can see that it's basically, here's the target star, nothing happens, and then it gets really bright as the lens passes along the line of sight, and then gets back to its normal value. And this happens over the course of quite a large period of time. But you can see the shift in the position of the object because it gets distorted by the intervening lens, and then you can see the change in brightness. And the change in brightness is the most when the lens is perfectly aligned along the line of sight. Okay, so that's what they saw. Here's like an image of the star field taken with the Hubble Space Telescope images. They observed this with HST over the course of almost a decade. Let's see, do they have, at some point it has, this is a gigantic paper, it's got 34 pages. But you can see here the images taken from 2011 up through 2017, and then there were follow-up observations presumably all throughout this period of time. So you can see this is the object that they're looking at, is that bright blob, this bright blob, and you can see how it changes, it gets dimmer over time. Okay, while the target that's next to it stays the same brightness. So this is the object that's being lensed. So when they did this, they saw this change in brightness, and then they use physics, they use equations that were derived a long time ago that tell you basically what are the properties of the lensing object given the change in brightness that you observe. And that is, well, the moral of the story is, so here's some more images. You can see how the image changes over time. What they came up with was, oh, let's see, take a look at this. So this is with a whole bunch of data. You can see all of these different telescopes were taking data, all the different colors, and you can see this big, gigantic lensing event. Okay, there's clearly some noise that came into this at different places, but you can see this big lensing event. And how long does it last? So the peak of the lens, you know, if we say that like this is the typical width, it looks like it lasted for about 100 days. Let's see, 100 days is this. Okay, yeah, so let's say it lasted 100 days. So that's basically the whole width of the base is about 100 days. Okay, and then this is zoomed in again at the data like right on it. That's pretty cool. I mean, there's some that are off, but for the most part, the data land right on the model. And this is like a 2-parameter model. All right, so from this, they can determine the mass of the object that's the mass of the lensing object. And what they ended up with, I'm going to go straight back to the top so we can just get it straight from the abstract. What they ended up with was a 7 solar mass black hole. We report the first unambiguous detection and mass measurement of an isolated stellar mass black hole. We used the Hubble Space Telescope to carry out precise astrometry of the source of the long duration 270-day high magnification microlensing event. So the lensing event was high magnification, and then they went back and looked at several different images from the HST to get the displacement of the source. Okay, but this is the important thing. The first unambiguous detection of a mass measurement of an isolated stellar mass black hole. The stellar mass black hole is important. So we have several different reasons why we believe that black holes exist. So for example, one of the main reasons that we understand that black holes exist was given the Nobel Prize not long ago. So that's black hole stars, galactic center. Here we go. This is the one that we want. So this shows the orbits of a bunch of different stars. Let me zoom in. Not what I meant to do, but okay, we'll go with it. All right, so these are the orbits of stars in the center of the galaxy, going around some point in the middle. And these stars have huge orbits. You can trace, well, they're on these orbits. You can map out the orbits. They're all different sizes. You can map out the orbits over time. So you just look at the center of the galaxy and you trace the positions of these stars, and then you fit an elliptical orbit to them. And from the orbits of all these stars, you can determine the mass of the object that's at the center. And based upon where those orbits, like how close those orbits get to the middle, you can put a constraint on the size of the object that they're orbiting. And so all of these things combine to say that there is some very high mass object in the center of the Milky Way galaxy. It's about 3 million solar masses, and it has to fit within something roughly the size of the orbit of Pluto. And the only object that we know of that can be that massive and that small is a black hole. So we've also seen the black hole image of the black hole from the very long baseline interferometry. So black hole accretion disk. So the image of the black hole accretion disk, this was taken using several telescopes spread out across the globe as an interferometer. So they basically treat the whole Earth as one big telescope and combine information from a variety of telescopes that are all spread out. And they got this image here, which indicates, one, that there's, so this isn't definitive proof that it's a black hole. That came from the stars' orbits. Well, even then, right, it could be something else, but it would be more exotic. The explanation that we currently have that's, it would require coming up with a new theory for creating an object right there when we have a perfectly good theory that predicts what it is. Okay, but this is the material that's orbiting around the black hole and how it gets warped. Okay, so we have some massive compact object in the center of the galaxy, and we can see that the disk of material that's going around it, the disk gets hot because of friction. And we can see from that disk of material that some of it gets lensed, and that's why it's brighter. Some of it's going behind, and so it gets distorted a little bit. We can't, for the moment, we can't really get much higher resolution than this because, now this is the M87 black hole. This is not the galactic center black hole, but it is the M87 black hole. It's the black hole at the center of a different galaxy that's got a, where we can observe this. It's a bigger black hole than the one in the center of our galaxy. That's why they look there. This is all consistent with the existence of black holes and consistent with the predictions of Einstein, which is where those predictions came from, where the black hole, the idea of a black hole came from. Here is a question: why are black holes so heavy? So black holes they're dense more than heavy. So you can have black holes of a variety of masses, but the density of the black holes is what's the real kicker. So they're super dense, but they can be, you can have a black hole that's the mass of a proton if you can get it small enough. You can have a black hole that's the mass of, in this case, 1 million solar masses, and it's a much larger region of space, but the physical properties, mass is just one parameter, and there's nothing that prevents you from having a black hole of masses that are arbitrarily small, except for the fact that eventually quantum mechanics takes over, and you have to worry about, does the quantum wave function of the particle fit within the radius of the black hole that you form from that particle? So I lied, I guess, earlier when I said you could have something the mass of a proton. That's actually not quite true. If you want to also have quantum mechanics function at the same time, then what you end up with is a mass called the Planck mass. So the Planck mass is the mass of, this is basically the real minimum mass of a black hole. The idea is if you form a black hole with something that is the Planck mass, then the Compton wavelength, the quantum wavelength of this object, will be the same size as the event horizon of the black hole. So the event horizon of the black hole is the region around a black hole. Here's this black hole. It's the region around the black hole where the escape speed from the black hole is faster than the speed of light. And the boundary where the escape speed is equal to the speed of light is called the event horizon. Every event in space that occurs inside the event horizon, its future light cone points towards the singularity, the black hole at the very center. Everything outside the event horizon can escape to infinity. Any event that happens out here, the light cone, which means the information from it, can propagate outwards and make it to infinity. And at the event horizon, that's where the transition happens between objects that can communicate with the rest of the universe and objects where their universe is the interior of the black hole. And the black hole, what most people consider like the surface of the black hole, is actually an imaginary line called the event horizon that separates those two things. So any quantum particle is going to have some corresponding wavelength, and like quantum wavelength, and the Planck mass is the mass where if you form a black hole out of it, then the quantum wavelength is equal to the size of the event horizon of the black hole. If you make the black hole with a smaller mass, then the quantum wavelength of that particle is bigger than the event horizon of the black hole, and then you really have to worry about quantum mechanical effects. Like, what does it mean when you can't localize the position of something inside the event horizon that formed around it? So, and that's why, we don't have a quantum theory of gravity yet, because we don't have a theory that can simultaneously deal with the event horizon size and the quantum mechanical effects. So this is the correct statement from, I misspoke earlier, the Planck mass. The Planck mass is actually not incredibly tiny. I think it's like 10 to the minus 5 grams. We can look this up real quick. Planck mass in grams, 2 times 10 to the minus 5 grams. Okay, so that's a microgram. It's 21 micrograms. So that's, it's not a trivial thing. A proton, on the other hand, is 10 to the minus 27, 10 to the minus 27 kilograms. So that's 10 to the minus 30 grams. And so this is 25 orders of magnitude larger than a proton. A proton mass, so this is in grams, the Planck mass is about that. It's a 2. And the mass of the proton is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30 in grams. So that's the difference. Here's the proton mass. That's the Planck mass. So back where we were with black holes. So we know that black holes exist from the galactic center. At least that is strong evidence for it. We see it from this very large baseline interferometry, looking at the accretion disk and the fact that it behaves the way that we expect it to behave. Another piece of evidence for the existence of black holes, and I think this is kind of the most definitive evidence, is the LIGO black hole detection. So it's the in-spiral of black holes that creates the gravitational radiation that produces the signal that we see in LIGO, which is none of these things. These are all artist renditions. Let's see if we can actually get the data. Here we go. This is the image that we're looking for. So this is the in-spiral of a pair of black holes. In this case, it's 2 roughly, I think 30 solar mass black holes. So 2 black holes, the mass of the sun. I'm sorry, 2 black holes, 30 times the mass of the sun, that are spiraling around each other and eventually merge. And this is the distortion of space-time, which means the distortion of the light rays that are coming, or that would be propagating through the space between us and this thing. That distortion shows up as basically a stretching and compressing of space-time by a tiny amount, by 10 to the minus 21 times 4 meters. That's small. That is smaller than the size of a proton. It's like 1/1000th of the diameter of a proton or something like that. So it's a tiny amount that it gets stretched, but we have the instruments capable of measuring that stretch. So this is really kind of definitive proof that these are black holes, because that's the only way to get these objects that are that close together. And we already know that the theory that these objects are compact enough that it would form a black hole even if it wasn't a black hole. So there we go. Okay, would I mind repeating what I just said about why we do not have a theory for gravity? Oh, isn't it 10 to the minus 24 grams? Did I do that the wrong way? You're right, it's 10 to the minus 24 grams. So this is too many zeros. You need to get rid of 6 of these zeros. So I stand corrected. Let's see, what I said, we do not have a theory of gravity. We don't have a quantum theory of gravity. So because we don't have a quantum theory of gravity, we can't simultaneously deal with space-time curvature and, okay, we do have a quantum theory of gravity, but it's, in my opinion, a little bit overblown. It doesn't make predictions that we can actually test, and so as a consequence, it's not really falsifiable. String theory is proposed as a quantum theory of gravity, but it's got a ways to go before it will be widely accepted as such. So a quantum theory of gravity is something that can simultaneously deal with the curvature of space-time, so meaning the region around a black hole, properly, like mathematically describing the properties of space-time around a black hole, and simultaneously describing the quantum nature of the particle itself. It's like, what's its quantum wavelength? Can you have interference, like black hole interference patterns and things like that from quantum measurement devices, and so simultaneously addressing the quantum nature and the space-time curvature nature of an object, that theory doesn't exist. These two theories are currently incompatible with each other. So these are all evidence for black holes, and the most recent evidence for black hole is the one that we just saw from this one, which is an isolated stellar mass black hole. First time it's ever been detected. And stellar mass is the important thing, or one of the important things here. So we've seen the supermassive black holes at the centers of galaxies that are like millions of solar masses. This is something that is much closer to the mass of the sun. It's 7 solar masses, 7 plus or minus 1.3 solar masses. Okay, now one of the first things I thought of when this black hole was discovered was, wow, that is exactly in the window where these black holes could make up the dark matter, or at least a portion of the dark matter. This paper came out in January. I think it was January 31st. Let me scoot this over. See, it should have the date. January 31st, 2022 is when it came out. All right, so let's take a look at what options there are for the dark matter. We believe that dark matter exists because we can see the effects of the rotation curves of galaxies, that stars orbit more rapidly than they otherwise should. If it's only the stars that are present, the galaxies should be flying apart. The stars are moving too fast for the gravity of the stars alone to keep it bound. And so that was, well, that and the same thing with clusters of galaxies. You have the same problem with clusters of galaxies. You have the same problem describing the growth of clusters of galaxies, like the growth of large-scale structure in the universe. All of these things point to the existence of dark matter, or something really unusual. But dark matter is kind of the standard model. The standard cosmological model includes a major component of dark matter. When I say major component, that roughly 30% of the universe total is matter, divided into about 5% regular matter and 25% dark matter. So one-sixth of the matter in the universe, according to the standard model of cosmology, which is the one that's most widely accepted, or at least the one that we compare everything to, 1/6 of the matter in the universe is regular matter, and the remaining 5/6 of it is dark matter. Okay, there are two main schools of dark matter. Okay, these are, so we know that of the existence of dark matter, and the two things that were proposed, so I'm going to say that we know these things, simply to say that the standard cosmological model includes these things. All right, some of these things are called WIMPs. These are called weakly interacting massive particles. And so this is going to be tiny subatomic particles that the universe may create for one of a variety of reasons. They may exist there because they're particles that just haven't detected. They don't couple to photons, and so they don't interact very strongly with things in the telescope. They might be some of the fundamental particles that we haven't detected yet. They might be supersymmetric partners to the standard model particles. So this gets broken down further into like supersymmetry. They could be like, what else do they have? Glue balls. There's like zombie something or other particles. There's a whole bunch of different possible WIMP candidates. Of course, everybody's favorite WIMP candidate is the axion. The axion is not something related to supersymmetry or the strong nuclear force. I guess it is related to strong nuclear force, but it's not something that's related to what most people think of as WIMP dark matter. The axion is a particle that was proposed to solve a completely different problem in the standard model of particle physics, and can also explain the dark matter. Okay, but there's a whole bunch, most of the particles that people think of when they think of dark matter particles for making a big dark matter detector and looking for these particles in space are other kinds of WIMPs from different models. The axion is its own kind of unique animal, which is, as I mentioned, it's my favorite of all the dark matter candidates is the axion. WIMPzillas, that's what the one I was thinking of, is that you might have WIMPzillas. WIMPzillas. Okay, on the other side of dark matter is, so these are tiny particles. The other side is massive compact halo objects, MACHOs. Okay, so massive compact halo objects. These would be massive objects that are very compact, so they have a large mass, but they don't have a large size. They're compact. And they exist in the galactic halo, and they're objects. And so that's where this comes from, massive compact halo objects. So these would be things that are flying around the galaxy. They're not made out of regular matter, so they can't be just like planets or something like that. We know that regular matter, there isn't enough regular matter in the universe to account for dark matter. So whatever the dark matter happens to be, it can't be made out of protons and neutrons. I guess very briefly, let me go back and explain why we know that. In the early universe, it's very hot and very dense, and there's a whole bunch of stuff flying around bumping into each other. One of the consequences of that is if you have a proton and another proton down here, if you have these two protons in a hot, dense universe, they're going to bump into each other and they're going to form deuterium. So one of the protons will spontaneously convert into a neutron. You emit some stuff, you emit like some beta emission, and you're left with a deuterium nucleus. You can still add more protons to the mix, and you'll get helium-3. You can add another proton and have it spontaneously convert and get helium-4. You also can add some of these things together and get lithium. Lithium is spelled with an L. So the light elements in the universe were created in the very early times when it was hot and dense, and you were getting nuclear fusion happening in the early universe. You can compare the relative abundances of all of these different elements to constrain the density of these particles. So if the density was really high, then you would end up forming things beyond lithium. You would get boron, and you would end up getting carbon and stuff like that in the early universe. If the density is really low, you might only get some small fraction of these things, or you may never get nuclear fusion at all. If the density is too low and everything is too far apart, then by the time the universe cools to the point where nuclear fusion can happen, the particles are already too far apart that they don't bump into each other. And so the temperature is low enough to allow nuclear fusion rather than the particles just bouncing off of each other, but the density is too low to have a high probability of a collision. So there's a window where the temperature is low enough for the particles to bump into each other and stick, and yet the density is still high enough for them to have frequent collisions to allow the sticking, to enable the sticking to take place in the first place. So that window puts a constraint on the overall density of regular matter in the universe, and we know that it's basically 4%. I usually, a rule of thumb is that it's basically 5%, because then everything rounds up to, it's 5%, 25%, and 70% for regular matter, and dark energy. Those are the numbers that are easiest to keep track of, and then you actually make, your second order corrections. But it's roughly about 4% of the energy density of the universe is regular matter, and so the remaining 25% of matter, the remaining 25% of the stuff in the universe, which is the majority of the matter, right? It's 5/6 of the matter, has to be something that is not made out of protons and neutrons, because if it was made out of protons and neutrons, it would have affected the relative abundance of the light elements. Okay. We know that this matter needs to be there, and so the question is, what's it made out of? We've already seen that it could be made out of WIMPs, which is stuff that doesn't participate in the formation of light elements. It could also be these massive compact halo objects, MACHOs. And one of the candidates for MACHOs, so these would be, the most common candidate would be a primordial black hole. So these are black holes in the very early universe that form right from the beginning. So you have a hot, dense universe, and here's a whole bunch of particles that are around here. And if you get a region where a whole bunch of these particles all come together and merge and form a black hole in the early universe, then this doesn't participate in the nucleosynthesis that took place later. And so you have this black hole that's just sitting around, gobbling stuff up, growing to some size, and then it eventually, escapes out into the universe, and at some point will collapse, like they will aggregate together and form the halos from which the galaxies themselves are going to form. It will attract the material into these halos, and the halos will merge, bringing their stuff with them, and then you get the star formation and the galaxy formation that takes place. So these could be primordial black holes, PBH, primordial black holes, because we'll see PBH in the literature that's coming up. This is basically the candidates for MACHOs. So what happened was, in the late 1990s, there were a group of people, a few groups of people, who were looking out into space, in particular towards the galactic center and the Large Magellanic Cloud. So here's us, right here. Here is the galaxy. You have the galactic center right here. You have the Large Magellanic Cloud over here. And they were pointing their telescopes towards the galactic center, the reason being that the galactic center has a lot of stars in it, and the Large Magellanic Cloud also has a lot of stars in it. And when you're looking at these distant stars, so those are your target stars in the galactic center. So we'll just take a look at the galactic center specifically. Here's all your target stars. And then you have these massive compact halo objects. So here's your massive compact halo objects passing along the line of sight. And as a consequence of them passing along the line of sight, your target stars will get brighter from gravitational lensing. And so there were a number of surveys that took place in the early, or the late, kind of mid to late 1990s into the early 2000s, of people looking for the gravitational lensing signature of these target stars from the from the MACHOs as they pass by. And the lack of observation of these objects passing by was an indication that, it puts constraints on the amount of dark matter that could be in these objects. So what fraction of the dark matter can be made up of MACHOs given what we observe in these microlensing surveys. So some early results on that, or the results of that came out. Yes, and these are all researched in our own galaxy because that's where we can see the stars. The distant galaxies are too far away to really resolve the individual stars to the point where we'd be able to do this kind of stuff. We might be able to see some Cepheid variables, but those are rare and particularly bright. So let me pull up. Okay, I have a few images. Let me pull this one up. All right, so this image is showing that's actually not the one that I want to show, but we'll get to this other part here, but it's showing the constraints that you get from microlensing. You can see on this side right here, it says microlensing, the mass on the bottom. So this is 10 to the minus 1 solar masses. This is 1 solar mass. This is 10 to the 8 solar masses, which is 10 to the 8 is what? 100 million solar masses. There's a better image. Maybe this one. That's not really the one either. All right, I pulled up a bunch of papers, and so they all have, okay, this is the image we're going to look at. Let me make sure that it's centered. And I'll describe what's going on in each of these limits. So here we go. This is the constraints that you get from these different searches. So this MACHO right here, Eros, I think is another one of these microlensing surveys. This is the MACHO mass. So in solar masses. So we have 1 solar mass down here. Now this extends way to the left. They have constraints down to planetary mass, like Jupiter mass MACHOs. 1 solar mass, 10 solar mass, 100, 1,000 solar masses. So these MACHO constraints are basically below 10 solar masses. So we know from the microlensing surveys that if the dark matter is made out of these MACHOs, and those MACHOs have a mass less than 10 solar masses, or much less than 10 solar masses, that it can only contribute a fraction to the dark matter, the necessary dark matter to keep the galaxy held together. And so the vertical axis here is the fraction of dark matter. So if it's 100% of the dark matter, then it would be at the top. If it's 0% of the dark matter, then it would be at the bottom. And if it's anywhere in between, then it's going to be in between. And so, for example, we can see that MACHOs from this one MACHO survey can constrain the fraction of the dark matter coming from MACHOs to be not more than, looks like 30%, if those MACHOs are 3 solar masses. So here's 1 solar mass, 2 solar masses, 3 solar masses. That's where this survey happens to be most sensitive, is at 3 solar masses. And we can see that the constraint from this particular survey is that not more than 30% of the dark matter can be made out of MACHOs. So it could be made out of MACHOs. You could have 5%, 10%, something like that, MACHO dark matter, and the rest of it would have to be something else. The rest of it would have to be, of course, axions or other kinds of WIMPs or something more exotic. Okay, so that is what we see on this left-hand side. There's some other images. I guess I'll show this one as well. It has the same shape. This one spans a little bit more in parameter space, but it's the same information. So we can see that here's the limits from, in this case, the Eros survey, which is also shown on there. And here you can see that the constraints go from 1 solar mass, so this is 1 solar mass right there, down to 10 to the minus 3 solar masses. This is Jupiter mass. So 10 to the minus 3 solar masses is 1 Jupiter mass. So we can constrain Jupiter mass, basically black holes, as not contributing more than 10% of the dark matter in the galaxy. So that is one way that we can constrain dark matter, or MACHO dark matter. There's another way that we can constrain MACHO dark matter, and that is by looking at wide binary stars. So here is the galaxy. Okay, pretend that it's got these MACHOs that are all orbiting around, and the MACHOs are going to be concentrated primarily towards the center because we can tell what the density profile of the galaxy is by looking at the rotations of the stars. And now you have a binary star system out here. Okay, and this is not just any binary star system. This is a very wide binary star system. Okay, so it looks like a smiley face or an Amazon logo, but it is not. This is 2 stars that are orbiting around each other. Now, if you have 2 stars that are orbiting around each other that are right next to each other, these 2 stars are hard to strip apart. These things are going to be right next to each other, and the only way to strip them apart would be to put something really massive kind of right between them and have some really strong interaction. Okay, and it's a small target because in some cases these stars can even almost be touching each other. These wide binaries are separated by something on the order of like 0.1 parsecs. So this would be, that's 0.1, there's a 1 in there. Okay, or even as much as, like a light year. Some of these things are pretty widely separated. So that's bigger than the solar, that's farther apart than the orbit of Pluto around the sun. So these are huge orbits of these stars, but they're still bound together. So these two stars are still orbiting each other. Now, what's going to happen over the course of hundreds of millions of years is that these stars are going to plunge in towards the galactic center, and then they're going to come back out, because that's what these stars do. And as a consequence, as they come towards the galactic center, they don't necessarily even have to get that close to the galactic center, but as they come in, they're going to interact with these MACHOs. Okay, and if you have really high mass MACHOs, say one of these MACHOs is 100 solar masses or 1,000 solar masses, so you have a pretty big black hole that's there. These wide binaries are going to come in and they're going to interact with these 100 solar mass black holes, and they're going to be disrupted. They're going to be broken apart. It doesn't take much to take two stars that are very, very loosely bound from each other to break them apart. Okay, and so what you can do is look at how many of these wide binaries are there in the sky, and if they're there, and the age of the stars is pretty old, it doesn't take that, things orbit the Milky Way galaxy on the order of a few 100 million years. And so if these things are older than like 1 billion years, then they've already made several passes through the center of the galaxy, or through the plane of the galaxy. And so they would have already had multiple opportunities to interact with these massive compact halo objects if they were there. And so it allows you to put constraints on the large mass MACHOs. The presence of these wide binaries that have survived multiple passes through the galactic plane or through the galactic center indicates, it puts a limit on the number of 100 solar mass objects that can be floating around in the galactic center. Okay, and so that, when we go back to this image here, that is these things. So this actually this is a slightly different one, so let me go to the other figure that I had. Wide binaries, right? That's this one right here. So these wide binaries, these are constraints on the prevalence of macho dark matter on the order of 1,000 solar masses or bigger, or like 100 solar masses or bigger. There was one, the constraints in the past used to be a little bit better, but there was one wide binary that for some reason a particular team in the intervening years said this one isn't a very good candidate, and so they removed it, and it loosened the constraints from wide binaries. But this basically shows that MACHOs that are 100 solar masses or bigger, 1,000 solar masses or bigger, can contribute no more than about 40% to the dark matter. Okay, so then there are other constraints that you can make that are basically the same arguments as these wide binaries. And so this one here, this UF dwarfs, so this is small dwarf galaxies. So small dwarf galaxies are also galaxies are dominated by dark matter, and so these small dwarf galaxies are dominated by dark matter, and you would get the same kind of effect where stars evaporate out of the system. They get kicked out of the system. So you have, where am I looking at? You have a small galaxy like this. It's got big MACHOs in it, and it has a bunch of stars in it. And those big MACHOs would be kicking the stars out of the galaxy, evaporating the stars, or exciting the orbits of the stars until eventually they start to dissipate. And so when you look at the ages of the stars in these distant galaxies, you can constrain the mass of any perturbing object that would be ejecting material. Okay. And so that is where this UF dwarfs, and the same thing with this Airy-2, that is a star cluster. The same idea applies to the star clusters, where now instead of a galaxy, you have a cluster of stars in our own galaxy. So instead of a distant but small galaxy, you have a star cluster within the Milky Way galaxy. And if there were MACHOs, then it would be ejecting stars out of that star cluster. And so the survival of those star clusters depends upon the presence of any perturbing object. So using this evaporation of small stellar clusters or galaxies gives you this constraint, this UF dwarf and this Airy-2 star cluster constraint. Okay, now what does this have to do with anything else? What this has to do with is the fact that the hardest place to constrain the presence of dark matter MACHOs is right here, around 10 solar masses. The weakest constraint we have on the presence of MACHOs being the dark matter is around 10 solar masses, and this is exactly the mass that we get from that rogue black hole that was just detected or just announced a couple weeks ago. So it's at 7 solar masses. It's right here. And so it's an example of something. It obviously is a Macho. It does contribute to the dark matter of the Milky Way galaxy. I looked briefly to see if there was someone who did a follow-up study that says, oh, given this information, what is the prevalence of, how much could this actually contribute to the dark matter, given that, we observed the galactic center for 10 years. We have, the probability of getting one of these things to cross is going to be some amount. The existence of an object that lands in this window makes it actually more probable that it can contribute some. So I didn't see that. They didn't do it in the study that announced the black hole itself. Maybe they didn't have time to do it or it didn't cross their mind. But I suspect that in the near future, we will get another study that says, okay, given this detection of the 7 solar mass black hole, what does it say about Macho dark matter? Those of us who really care about dark matter, that's the first thing that I thought about at that mass range. Because the black hole itself, black holes have been discovered, but something at 7 solar masses puts it right in this window where we are least sensitive to being able to find objects that are like that. Let me pull up, there's another constraint that we can put on Macho dark matter that is not on this one. It's on this one right here. So what's showing up on this graph? It's the same graph. It's got the same mass of the Machos here. Here it just listed as primordial black holes because that's the main way that you would make these kinds of things, the prevailing mechanism by which you'd make them. And then this on this axis shows the amount of that the primordial black holes can make for the total matter in the universe. So in this case, it's not the total dark matter, it's the total matter. You'll notice that 5% is cut off at the top. That's because we know that 5% of the matter in the universe is regular matter made out of protons and neutrons. That comes from the Big Bang nucleosynthesis that I described a little bit earlier. So we know that 5% of the total mass of the universe is up here. And then, wait, is that what they're talking about here? Hold on, I may have misquoted that. Because this actually has total matter and not total energy density. So, okay, ignore what I just said about that, but that's the first thing that came to mind. Dark matter fraction. So somehow this dark matter fraction, oh, it does go up to 100%. I was wrong. It does go up to 100%. I guess this is, I don't know, I don't understand this axis here. I do understand this axis over here. So that's the one we want to look at. So 100% of the dark matter up here, and then it's got this bound that goes up a little higher than that for some mysterious reason that I'm sure that the authors understand, and but it's a new representation for me. But here is the percentage of the dark matter up to 100%. We can see this again, the Eros study. So that is the microlensing signature. We have here's this Eridanus 2. That's the star cluster evaporation signature. We have a few other things that show up here, which is it's related to, we would see a signal, we would see the effects of these things on the cosmic microwave background radiation, which we don't observe. So that can put hard constraints on things that are like 1,000 solar masses. What's not shown here is the wide binaries, but they're basically along these same, the wide binaries aren't as stringent as the star clusters constraints are. And then this one, this particular study, it does show the detected LIGO black holes. So these are black holes that have been seen to in-spiral around each other. So we know that black holes exist at this mass because we see them in the LIGO detection, LIGO detections. So this is the range of black holes, the range of masses of black holes that have been detected in LIGO. They're 10 to 100 solar masses. Most of them have been in the 30 or 40 solar mass range, something like that. And then what's shown here is supernova lensing. So here what happens is you take a galaxy, a very distant galaxy, and you have a supernova go off in that distant galaxy. So here's your distant galaxy, and it's got Machos. So here's all the Machos in that distant galaxy. And you have a supernova go off. So a supernova blows up. And when the supernova blows up, it's got some probability of being lensed by a Macho within that galaxy. So the supernova blows up, the light leaves that galaxy, and it has the opportunity to be lensed by a variety of different Machos within that galaxy. And as a consequence, if you look at the distribution of the brightness of these supernovas, so you say some supernovas are dimmer than others, some supernovas are brighter than others. If there's some lensing events, then what you'd expect to find is instead of having something that looks like this, a normal distribution with some less and some brighter than average, you would expect a distribution that looks like this. So here is your curve. you got this, and it comes out here, and then you get a lensing, like a tail of lensing events out here. So these are really bright objects that happen to line up with a lensing Macho, and therefore they appear brighter to us than they would otherwise be. Okay, so then what this group did is they studied the distribution of the supernova data, looked at this distribution, and looked for a tail that sticks out the end. At least that's what I understand that they did. And so by doing that, they can constrain, they don't see anything out in that tail, and therefore they can constrain the presence of Machos by saying, if there were Machos at this mass, then it would show up in the lensing signal with some frequency. We don't see any, and therefore we can put a constraint on their existence. And so that's this constraint that shows up here. But again, all of this still points to the fact that the hardest place to find Machos is right at the mass of the black hole that was detected by this group using the Hubble Space Telescope. So I'm not convinced that Machos are the dark matter, but it is intriguing. You know, maybe it is, or at least it can't be 100% of the dark matter, but maybe it is 30% or 40% of the dark matter. And that actually changes a lot. If the dark matter is, you know, even 10% of the dark matter is made up of Machos, then that changes all of our constraints on the other forms of dark matter that people have been looking for. So the dark matter that people have been looking for from WIMPs or axions, they assume that all of the dark matter is whatever that substance is, and therefore their limits are placed based upon that assumption. And so if you can have a third of the dark matter actually be something else, then all their limits are off in terms of their ability to constrain things. Or, yeah, so their constraints on the properties of the dark matter are going to be different because their assumptions are no longer valid. So there we go. This EROS, that is a something lensing survey where they were looking for the lensing of microlensing signals towards the galactic center or towards the Large Magellanic Cloud. I don't know specifically what their targets were, but it's all basically the same type of study. So that is Macho dark matter in all of its power and glory. The constraints we get from Macho dark matter and how that Macho dark matter is, at least how that black hole that we just, when I say we, that this group just detected a few weeks ago, might have interesting things to say about Macho dark matter in general. All right, does anybody have any questions? What is my thought? That this could mean that there are massive black holes that we are not good at detecting that makes up for percent. So what is my thought that this could mean? Yeah, so I think this shows that there are indeed there's at least one of these things in the galaxy. So it's not 0%. There's at least one of them, and given the amount of time we've had to look for them, it might mean that there are many others. And so it could be, thank you for that sub, it could be something that indicates that, you know, it doesn't exclude, it actually supports the idea that there could be a significant fraction, or sizable fraction, I won't say a significant fraction, sizable fraction of the dark matter is actually made up of these stellar mass black holes. So it's more than a solar mass, but not supermassive. One thing to point out with this is that we don't know how this formed. This is also in the range where you could form these things from stars. And if this black hole formed from stars, then it is definitely not a dark matter candidate. If this black hole formed from a star, then that means that before it became a black hole, it was actually made out of protons and neutrons, and we already have constraints on the amount of protons and neutrons in the universe. So if this black hole came from the early universe prior to the formation of the light elements, then it would definitely be a Macho. So there is this question that remains, and I don't know that there's any way to resolve the issue. The question remains, did this black hole come from a star, in which case it's not dark matter? At least it acts as like dark matter today, but it doesn't count in the dark matter budget, because if it came from a star, then it came from protons and neutrons to begin with, and then formed the black hole later. And if it came from protons and neutrons to begin with, then it's not dark matter. However, if it is a primordial black hole, something that came from the early universe prior to the formation of the light elements, then it is a dark matter candidate and was never a star. So I guess the only way for us to tell what it is would be to find several of them and then see if the statistics that we get match our understanding of early star formation or of the early universe. How come, what do we got? Let's see. So that's my thought. the constraints for other dark matter candidates get tighter or looser. So the constraints get looser. So if this, let's pretend that this is a primordial Macho, so it actually is a primordial black hole. Then that means that some fraction of the dark matter is actually made out of these primordial black holes. And therefore, the constraints that people have placed assume 100%, but if it's only, okay, so let me show you what the exclusion limits would look like. So if you look at the WIMP dark matter, so here's like the mass of the dark matter, and here's the cross section is typically how it's plotted. And so you'll have a survey that says, oh, here's our constraints on the presence of my favorite WIMP dark matter. And this is going to say that, you know, here's the constraint on the cross section, the interaction cross section, and the mass of the particle. But this assumes a 100% dark matter made out of this WIMP, because you're basically making a detector, putting it on the Earth, and letting the dark matter hit the particles in your detector, like letting the dark matter particles hit your detector and then show up. And so you're assuming what's the abundance of dark matter particles, and these all go on the assumption that 100% of the dark matter is made out of these particles. So if now all of a sudden only 50% of the dark matter can be made of these particles because the other 50% is Machos, just to pull out a number, then that implies that all of these limits have to go up, presumably by 50%. There might be some density calculation that goes in here that makes it the cube root or something, but you're limiting, instead of being 100% of the dark matter, now it's 50% of the dark matter, so all your limits, sounds like it has to go up by a factor of 2. So there's that. One of the things, especially with axions, this is a big problem, because when they're doing axion searches, they basically stop at the dark matter composition. So they make an observation, and as soon as they hit the dark matter limit, then they go to the next observation. And so if the actual detection of the dark matter would be a factor of 2 lower than that, they're never going to see it. Okay, let's see. So the constraints on dark matter from other candidates gets looser with this. If this is an actual Macho primordial black hole and not a star that turned into a black hole later in its life. Do black holes completely evaporate? And if so, do they destroy matter in the process? Black holes can evaporate. That's through Hawking radiation. Does it destroy matter in the process? The matter was already basically destroyed, but the quantum information is not destroyed. To the extent that you can do black hole thermodynamics, the quantum information, meaning the total number of bits of information stored in the quantum state, like the conserved quantum numbers, as that information comes in, the Hawking radiation carries that away. So Hawking radiation carries spin, it carries polarization, it carries the frequency. And so this isn't my area of expertise, but the idea is that the information can escape if it comes out, even if it comes out in a different form than it went in. So it could go in as television sets and come out as radiation. So does it actually destroy matter in the process? We don't actually know what happens to the stuff once it crosses the event horizon. There's no way to know what happens to the stuff when it crosses the event horizon. Let's see. Is it something to do with rising gravity and spinning tops? That I cannot say. Sorry if it was already covered, but how is this one specific rogue planet detected? So this rogue black hole was detected by looking at the lensing of a star in the center of the galaxy. How do we map out galaxies and know the distances to those galaxies? So the distances of galaxies are mapped. They're measured using what's called the distance ladder. So basically what happens is some stars we can triangulate to. So here's the sun, here's the Earth going around the sun, and you have a nearby star and you have a bunch of distant stars out here. And we can measure the distance to nearby stars by looking at what's called the parallax angle here, which is where does this star appear in the sky relative to the background in January compared to where it looks in the sky in June, or just, is it July? It must be July. Yeah. January to July. So you see that you look at it 6 months apart, you measure this angle, and then you can use your trigonometry to calculate the distance. So once you've calculated the distance to a large number of stars, up to this point, it was something on the order of 100,000 stars from the Hipparchus survey. Gaia, which is currently operating, has changed this to like 100 million or a billion stars. Gaia is like a huge leap forward in our understanding of the distances and therefore the structure of the galaxy. But we can measure the properties of stars to certain distances, and then we can use, now that we understand the properties of stars that are within this volume that we can measure, then we can map it onto more distant stars. So now, if you look at here's the galaxy. So we can measure the distances to like these stars, and now we can use our understanding of the properties of these stars to measure the distances to those stars and to these stars over here. And then in doing that, then we can measure the distances to, so then we take that information and map it onto distant galaxies and say, oh, we can see these properties of objects in this distant galaxy, and we can extrapolate from our known measurements to how we calibrate things in the galaxy, in our own galaxy, and how does that map to things in distant galaxies. And then we can say, okay, what are the properties that galaxies have, and we can calibrate a distance measurement to distant galaxies, not using stars anymore because we can't resolve individual stars, but we can resolve regions of gas. So like a big cloud of gas that shines pretty brightly, we can measure those clouds of gas on distant to distant galaxies, and that gets us even further. And then we can say, okay, we can't resolve these distant gas blobs anymore, but we can resolve supernova. So when you have a star explode, it gives off a certain amount of light. And so we can measure the distance of galaxies based upon our understanding of supernova explosions. So there's a series of interleaving length scales that we can measure the distances by relying on the previous length scale. So nearby stars goes to distant stars goes to different blobs of gas, distant blobs of gas goes to other distant blobs of gas. That gets us to galaxies as a whole, and that gets us to supernovas. And so we kind of string them together based upon these measurements. So that's the distance ladder is what that's called. So that's how we can measure the distances to distant galaxies, is by using this distance ladder. Rogue as in, so when something is rogue, it means it's not bound up into some collection of something. So a rogue planet is a planet that's not bound into a planetary system. It's just floating through the galaxy. Let's see. Okay, so that is Macho dark matter. Any questions about Macho dark matter or any of the other stuff that we've covered? So otherwise, I need to, Cepheid variable is one part of the ladder. Yes, so Cepheid variables was kind of the first extrapolation from our understanding of nearby stars to measuring the distance to another galaxy. So Cepheid variables were used to measure the distance to the Andromeda galaxy. How something was a two-parameter model. Okay, so what it means if something is a two-parameter model, probably a better example, it might be a three-parameter model. So, but the best example I can give for why it's important that something is a two-parameter or a three-parameter model is the following. So if you look at the cosmic microwave background radiation, so the temperature spectrum, so you look at the spectrum of light coming from all different directions of the sky, and you get a curve that looks something like this. Or actually, that you don't get a curve. What you do is you get a bunch of data points. So here is the intensity of the cosmic microwave background radiation, intensity as a function of wavelength. Is that right? Yeah, as a function of wavelength. And they made a bunch of measurements. So here's all the data that they made, that they observed. This is with the COBE spacecraft. This is what won the Nobel Prize back in the early 90s. Okay, so here's all the data points. Now there's a variety of different ways you can fit these data points. One of them would be that you have a big polynomial, like some function of x that is a plus bx plus cx squared plus dx plus blah, 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 and x cubed and x to the fourth. And you can make this polynomial function make almost any shape that you want. And if you have, let's say that you have 100 data points that you need to fit, you could have a 100 parameter model that goes exactly through every single data point. So you could have a 100 parameter model, so like 100 terms in your polynomial or something like that, and it goes through every data point right through the center. Okay, and if you did that, then people would look at you and say, you didn't do anything. All you did was say, here's the value of each of these points. There's no new information because you can't reduce the number of knobs that you can twist to be less than the number of data points that you have. And so if you have 100 data points and you say, okay, I have a polynomial with only 99 parameters, then it might not go exactly through every point, but it'll get closer to going through every point. Okay, sorry, I apologize for the shakiness of my curve here. And so one of the things that's most impressive about the cosmic microwave background radiation is that there's only one parameter. So there's a class of functions called it's the Planck distribution. So the Planck distribution is something that looks like this. Okay, it looks like the shape of the data that we're taking. And it has one parameter. That parameter is the letter t. And for low t, small values of t, the curve looks like that. And for large values of t, the curve looks like this. Okay, so it's a family of functions that has one single parameter. Everything else is a physical constant. It's e to the minus something, 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 1 over that, minus 1. There's a Boltzmann's constants in there, Planck's constants in there. There's probably a over hc in here, and there's a lambda to the fourth and something like that. But there's one parameter that you can tune. So there's only one knob to tune, and that is t. And so by mapping or by matching the observed data from the Cosmic Background Explorer from COBE, so here's all the data points, they put a one parameter model in, and it went through all those data points, like almost. It was so good. Might as well pull it up. So when I say it's a one parameter model, it's one knob that you tune and it goes through all the data points. For these other ones, it's like a 3 parameter model. So you have this series of data points that go like this. I don't know exactly the number of model parameters. It's the distance to the source, it's the distance to the lens, it's the mass of the source being the most important one. And then you have probably a few other small parameters that deal with instrumental uncertainty and stuff like that. But the physical parameters, the ones that aren't nuisance parameters, that deal with addressing systematic problems with your instruments, but the ones that are actually involved in the astrophysics, it's a small number. And so you have this curve that's not a trivial curve to fit, but it only has with only a few knobs to turn, you can put tight constraints on what the values of those parameters are. If we look at the COBE data, so let me go to COBE microwave spectrum. It looks like this. Okay, this is not a particularly zoomed in image, but here, maybe this one will do a little bit better. Yeah, it's basically the same. Okay, so these are the data observed by COBE. And the curve, it's one parameter, and the curve goes through all those data points. And in fact, typically when they show the COBE data, they have to make the error bars bigger so that they'll even show up on the graph, because the error bars are actually smaller than the line that goes through the data points. So it was an incredibly tight fit with a single parameter to go through 100 data points. So that's pretty cool. Would there be thousands of black holes in our Milky Way central region, supposedly? Yeah, there could be thousands of them. We just don't know. So I didn't see a study about, like, what does this imply? Now that we've observed one of these 7 solar mass black holes, how many does that imply that there actually are? So that will be something that I can't imagine many months going by without someone doing that analysis. Let's see. The day of the year, do the measurements of the star depend on the place of the star according to Earth's orbit? Yeah, so it's in that thing that I showed where you're measuring the parallax. You're measuring the position of the star at 2 different points in the Earth's orbit. You're basically just using geometry, like right triangle geometry, to measure this distance. And so it's the different perspective that you get from one side of the Earth's orbit to the other side of the Earth's orbit. Well, everybody, I appreciate you stopping by. I will be back, should be back next week. That's all I got for today.